Okay, well, why don't we go ahead and let's get this afternoon's program underway. On behalf of Dean Hurt and the entire faculty of CED, we're very happy to welcome all of you to our CED Fall Lecture Series. It's great to have so many students and faculty and good friends and distinguished alumni with us. And I can tell you, you're in for a very special treat today. Today's speaker is nothing short of remarkable. It's a real privilege and a rare opportunity to have someone address us today who not only pioneered and gave birth to an entire industry 6 decades ago, but who continuously for the last 60 plus years plays an active role in leading and evolving the entire industry. It's just nothing short of remarkable. And I can tell you at 85 years old, he shows no signs of slowing down, and in fact, quite the opposite. You're about to hear in his presentation this afternoon, which is entitled Think Big on GIS, on size and scale and GIS and geodesign. So I had a bunch of notes here to use. I don't need them. Carl Steinitz needs no introduction to those of you who've been working in GIS and geodesign for years. But for the few of you who may not know, he is the Alexander and Victoria Wiley Professor of Geodesign and Landscape Architecture at Harvard Graduate School of Design, and also Professor Emeritus there. He's also done pioneering work at the Harvard Lab for Computer Graphics since 1965. And since those times, he has conducted hundreds and hundreds of workshops, seminars, presentations, and projects all over the world. And his scholarly publication list and list of awards and recognitions is too extensive to even begin to talk about, but I can tell you it would just about cover this entire wall. So on a personal note, as one of his students now exactly 50 years ago, yikes, 50, Carl, he motivated and inspired all of us to work very hard to reach for the stars, be the very best that we can be, and probably the most significant gift of all was to instill in us this notion, this vision, that we are actually students for life, not just after we graduate. That's a gift, a true gift, Carl, that continues to keep giving throughout our entire lives. So we're very, very grateful for that. So, if you would, ladies and gentlemen, please join me in welcoming our distinguished guest lecturer, Professor Carl Steinitz.
I'm really glad to be back. The University of Georgia was the first university that invited me away from Cambridge, Massachusetts. I've been here many times, spoken with many faculty, many deans. Alan Stovall was the person who introduced me to grits. And I didn't take to them. I'm going to give a talk aimed at the faculty. The students should pay attention, but don't take it too seriously, because I'm going to go really fast. And you can take pictures, but the slides are here. Get a copy. Nothing that I do is copyrighted graphically. Use it, think about it, throw it away if you want to, but that would be very foolish. I don't think that the people at a university generally understand what its faculty is capable of, and especially young students. So I decided simply to honor these two people who I met in the 60s and who were extraordinarily adventurous. Gene Odom basically created modern ecology. Hubert Owens created the largest department, school actually, of landscape architecture in the world. Was then, still is. It's a hell of a lot better now than it was in 1960, when the University of Georgia was a second-rank university, and it's now a first-rank university. And that's basically because they looked outside. Georgia was one of the first universities in its Department of Landscape Architecture that had European faculty members, and faculty members who were not good old boys. That's very, very important. And it's because of the international, global outlook of these two people. It also was a joint school between ecology and landscape architecture, working across scales which are much larger and much smaller than most of you are working and thinking about today, and certainly with a much longer outlook in terms of time. The vast majority of what I see on the walls here is for tomorrow. But tomorrow, you're not going to be students. You're going to be in charge, and the world will have changed. And the question that really I'm talking about is, what are you going to do when your education doesn't prepare you for the global changes that are going to occur here? That's an interesting question, and it's an important young person's question. So the audience is the faculty, because the faculty decides what you learn. And if what you learn is today, that's not unimportant, but it's not sufficient. If you go away from my talk with that in mind, you're a winner. If you don't go away, you still may be a winner. But if you don't have anything in your mind, you're a loser. So these two people were important, and not just to the University of Georgia. I'm going to talk about size and scale in geodesign, and I use the word geodesign as a rubric for things that are bigger than having a client, a site, and a program. And the vast majority of your work, especially if you're a young student, is here's a site, here's a client, and here's a program. And the vast majority of landscape architects do exactly that. And half of them are the problem, and half might be the solution. But the real world works with indecisiveness. It doesn't exactly know what the site is. It doesn't exactly know who the clients are because they're not born yet in some cases. And they sure as hell don't have a program because nobody can predict the future totally. And those design problems will affect the immediate design problems. And if you can't think about those design problems, you're not preparing yourself for the future. It's as simple as that. The question that it remains is, how do you do it? And that's what I want to talk about. First of all, Galileo, 1638, in Latin. Many devices which succeed on a small scale do not work on a large scale. This is my shorthand for this problem. Now, these are scales, and 90% of the world uses scale and size synonymously. So most people say, that's a small project, and that's a small scale. But actually, that's a large scale, because it's closer to the real world. So if you're a cartographer or an engineer, that's a small project and a large scale. That's a big design project, and it's a small scale. Put that in your heads, because if you talk to engineers, ecologists, and other scientists, that's how they use the word. And designers usually use it wrong. The best definition of design that I know is Herbert Simon's in his Nobel Prize lecture. This is a polymath. He was an unbelievable intellectual in the end of the last half of the 20th century, professor at Carnegie Mellon University. He said, everyone designs who devises courses of action aimed at changing existing situations into preferred ones. You don't have to go to the design school to learn how to design. Everybody does it. Everybody is capable of it. Anybody who thinks ahead a little bit is making a design, whether it's mental, physical, drawn, built, doesn't matter. It's the idea that you're thinking ahead for something better than what you've got today. And you can call it whatever you like, a drawing, a plan. It's basically describing the word design, which is both a noun and a verb. Design is a verb, it's a process. It's also a noun, it's a thing. But the things vary and the process varies. And Another one of these things that most people think. You think that because you could design something at one scale, that you could design something at any scale. That's not true. There's a certain scale at which you don't know enough, and it goes both ways. The scientist who works here tends to fail as he moves this way or she moves this way. The designer who thinks we're going to go this way starts to fail around here when they don't know enough. And there's a class of problems in the middle which is very important, which requires both. But the more you go out there, the more the scientists will lead. The more you go out there, the more the designers will lead. And you're actually turning your educations that are backwards from each other. The reason that there's no ecology group in the school is because their process was different and their language was different. And they couldn't figure out that this was the design scale that they had to work on together. And the question of what does what, who learns what. If the ASLA thinks landscape architects are the stewards of the landscape, and it does, it says so, then why aren't they working here or here? That's where the landscape is. It's also here, but it's not only here. The founders of the profession of landscape architecture, why you study history. Loudon, Linné, Olmsted, Geddes, Warren. There were many others, some women. But these are 5 men, all white. They designed gardens, all of them. But Loudon made a design for the whole London region. He couldn't possibly have done that the same way he designs a garden. That was done on site. These were done on site with the client. These were not. That's all of London. That's the expansion of Berlin. That's the largest piece of private land at that time in America. And modern forestry came out of that site. That's Madras in India. And that's the whole United States of America, published in Landscape Architecture magazine in 1923. All of the United States of America, made with 400 plastic overlays, all drawn on a light table. Those are landscape architects. Brian Orland, Tom Fisher, and I founded an organization to think about larger projects. And we did that because we agree that the most important design problem is the whole world. Think about it as a design problem. We do. And we set it up so that the people who are in the collaboration would share assumptions and share ways of thinking about the work that they're doing, so that we could talk to each other. And my talk is going to show things that we've done here, part of that. Let me read this, because I think it's worth it. I think so. The most important design problem facing us today is the whole planet. Global conditions are likely to change in fundamental ways, and in this century and in your lifetimes, not mine. What is really needed is a reconsideration of how designs for the future are made and implemented. These designs need to think far beyond single system fixes, meaning the landscape as a single system. That doesn't mean somebody doesn't have to fix the landscape. And you need to know a lot to do that. But it means that you have to work with other people who are working to fix other systems that relate to your system and yours relates to them, to make any sense at all at a size that makes any sense at all. We have to integrate traditional and innovative practices considered across at least 6 major systems: water, biodiversity, agriculture, and forestry, energy, transport, and urban development, and for at least a geography incorporating the immediate water and food supply region of any city. Globally, these vary greatly. Many also need to consider drought, fire, migration, and unhealthy overcrowding. And this presents a very complex design problem. It is also profoundly political, because today's people have to decide to pay the costs of benefits for themselves, but also for future generations. That's actually important, because if you don't do it now, they won't. They won't have anything, a lot of people. We founded the International Geodesign Collaborative for all who want to join in addressing such important design problems. The first 50 of these show that no single innovative solution for any single system will be globally adopted. Some will be locally and regional considered, but those selected will all be adapted and integrated with other locally adapted systems. In other words, people are thinking about global policy for climate change and other things, but when it hits the ground locally, it's all going to be adapted to local conditions, and those vary enormously when you think about the world. I mean, you have people here who are not from Athens, Georgia, and who don't think the way you'd think if you're from Athens, Georgia. What now? What are they learning? How does it work when you're in a school where you're a stranger, a real stranger? What are you learning? Why do you learn local plants when you're from someplace that has deserts, for example? It's a very complicated educational problem for the faculty. If innovative digital technology can be helpful and effective, fine, but it's not the primary need. The real need is educated and effective people who understand how to work collaboratively, with most working locally, some regionally on these critical issues, and a few working globally. But all are needed now. Now. If you don't change in your lifetimes soon, change will change you. Again, it's as simple as that. We have a generic problem. The generic problem is, how do we organize? How do we get it together to conduct the very beginning and strategic stages of designing for longer-term change in a very large, multi-jurisdictional, multiple system, multiple client who doesn't agree with each other, relatively unpredictable, and contentious context, and one which should not become a zero-sum game. A zero-sum game is where America is first and everybody loses. That's a zero-sum game. Or you win, she loses. That's a zero-sum game. And design could be that, but it shouldn't be that. And why geodesign? And why negotiation as a design method? In other words, let me be very blunt. I don't care what you think, but I care that you are part of we and what we think. All right, whatever we are. And you have every right to make your views known, but you don't have your right to impose your views on me. We have to agree. And as long as that's understood at a certain size, it's a political process in the appropriate manner of it, and it has all kinds of problems. But your inspiration is only one of a set of ideas, because he, she has some, and he has some, and he has some, and she has some. And we could pick a winner. We could pick his design as the best one and build it, but then it's a zero-sum game. And she may have had better ideas on some of your design, which makes negotiation sensible. And as long as the project gets bigger and bigger and bigger, that gets more likely, more likely, more likely. And it means working different ways for different sizes. When fundamental conditions are changing and big data-based models predict future problems, the end game of our work still requires a purposely designed spatial temporal strategy for future action. And this is necessarily a political process among us, among scientists, designers, politicians, anybody who's involved in public affairs, or private affairs for that matter. Design occurs at different sizes, scales, times, that says time under there, and complexities. Design cannot work well in separated, sorry for the spelling, in separated silos. If you're given a project and it has a client, a site, and a program, and you bound your problem solution by the site, you're making a mistake because you don't know what's across the boundary. It can't work that way. Different sizes, scales, times, and complexities necessarily interact. Necessarily interact. And if you don't understand that, go back. And you're designing, let's say, a park along a river with office buildings where there's no office building here, but they're building an office building, therefore they're going to design a park here, like Michael van Valkenburg had to do in Pittsburgh. And you don't realize that somebody is figuring out how to manage water in the Susquehanna River, and they do a bad job, you're in real trouble. Oops, go back. Over time, design must interact globally to locally to globally. In other words, some of us begin here and go this way and then go this way. Some begin here and go this way and this way. And we come together at different points. But whatever point we agree on that we're going to study, we need to do at least this one and this one. If we're working here, we need to do this one and this one. So these relationships go up and down in size and up, down and up in scale. And that's terribly important. Related to size and scale, the ways we work vary. Most of you are down here, dealing with individual and small group designs. Most undergraduate programs in landscape architecture are exactly here. And most may go up to here. They probably do. Most don't go up to here. Almost none of them go up to here, and nobody, except in a very few places, goes up here. But the scientists have a different perspective. The scientists believe that what they're doing is true anywhere. And they're trained to think that way. So what they do is they may talk about ecology up here and move themselves down here through modeling, and they have a tough time with small designs. Very interesting. And the product of design work at different scales, these are individual adaptations to the idea of garden or park. They're all gardens. Seen up here, they're all green spaces. Nobody cares what the design is when you look from this point. They don't know what the design is. There's 50 million gardens in the world designed by landscape architects. Seen globally, they're ecological systems, at best. Seen at this school, they're really important and very different and very nice. But when you get up here, it doesn't matter anymore. Similarly, when we're predicting over here that the trees may change in Georgia, it may not matter to you very much in the short run, but it might matter very much in the long run. So these relationships are there, but it's different lenses that we're looking at. Some of these relationships are top-down. An international treaty affects people at home. If we banned fossil fuels because it destroys the atmospheric climate, it would affect your car. Some things go this way. There are things that people do that affect international treaties, like switching to electric automobiles. And the real problem is that it goes both ways. And how do you design at one scale when things are changing upwards and things are changing downwards, and you have to think about those relationships and those if you're working here? But you do have to think about those. And it's not making your studios easier, it's making them harder, but it's making them better. And ultimately, you have to decide where you are in size and scale, realizing a broad generalization on my part, that if you're coming at it from this side, in your mind and in your educational structure, you're dealing as a design profession with a very similar attitude to architects, urban designers, engineers is a design profession. You might argue that lawyers and bankers have a design profession, by the way. That you tend to have here high public and political understanding. People know their neighborhoods. And you tend to work on demand-based offensive strategies. In other words, you're given a client, a site, and a program, and you said, make a design, and you do it. You don't say to yourself, why are we thinking about doing this stupid project? Which it might be. And you work directly with the people of the place. And you focus your work on probably how you organize the site and what it looks like or feels like, with expression given much too much weight. Much too much weight. Coming at this project of the world from this side, you have a whole different situation. Oh, and by the way, these things and the effectiveness of the design professions tend to decline as the project gets bigger, when you realize you don't know enough. It's just hard. The scientists have a different perspective and a different problem. They're out here seeking scientific understanding, which tends to be data-based on the present and the past. They have a tough time thinking about the future. But if they do, they tend toward supply-based defensive strategies. In other words, what's important and we need to protect it. And they tend to have geographic sciences, anything with ology at the end. And they rely on data, on information technologies, sometimes limited by satellite technologies. In other words, they can't tell you one person from another because it doesn't show up on their database. So they have a different perspective, but they'll be the perspective that treats all of these gardens as the same out here, and they'll come at you this way, while you're trying to come at them this way. And the problem is that these things have to be part of this, and these things have to be part of this. And that's true regardless of what scale. If you don't understand the science of soils or of vegetation, you might be in trouble picking the right plants for the right soils here. And if they don't understand that the local people will change policies globally, they're in trouble making global policies. So it's not an easy problem. And the language that we use is different. These are all the things. The methods of design, they have to adapt to different sizes, scales, times, and complexities. Out here, I've been in a lot of schools, and I really understand how faculties and students interact. Out here, there's an assumption of certainty. It's my design, I know what I'm doing, which is surely not true most of the time. But there's the assumption of certainty. And serial sketching works. You you make a mark, you get 2 marks, 3 marks, 4 marks, and eventually a design comes out. It really does work. A design comes out. A different design comes out. And you can always change your mind. It works. It doesn't work out here. I mean, who cares what your sketch was for the world? What an absurd thought. But I've seen people try it. In the middle scale, somewhere in here, and these are fuzzy boundaries, diagrams work. Diagrams really do work out here. They also work here, and they sometimes work there, but they really do work in here. And it's based on the idea of uncertainty. There may be 5 different versions of a road system, 6 different versions of an open space system, 15 versions of a housing system. And then you start to put them together and eventually say, yeah, that works, let's get that done. And then you may choose to go this way. But out here, you basically are trying to figure out the rules without knowing what the future is. And then you either build rule and mathematical models and try to say, what does the future guide us toward believing if we believe our rules? And these 3 approaches, between certainty, uncertainty, and knowing the rules but not knowing where they're going to lead us, is the intellectual groundwork that we have to muck around in, which makes it, by definition, a collaboration. I mean, you here, if you have some uncertainty, might want to work here. They also might want to work here, but they, to know their rules, need to know what's going on here. That's where the rules come from. And you got to organize it. And this is one of the important parts of what I'm going to do. As you go in this way, the actual organization of the design projects changes. And don't believe for a minute that it's one person, one design all the time. It's not. If you're working here, you might have a client. It might be a family. It might be a corporation. It might be anything. But there's a few people that you need to talk to. You might have a professional group that has one designer or a small firm with 1 or 2 consultants. And when you talk to these 3 people, they may have 4 different sets of priorities, or 2, but not 1. Not 1. They're designing a house. Brian is designing a house. He has to agree with Martha and his grandchildren, all right? I understand that. I've done it, all right? So this is Martha's design. This is Brian's design. This is 2 unknown grandchildren's design, all right? And he's got to design the damn thing. So he has requirements. They have priorities. He has to figure out what their priorities are. And he say, you know, I'm going to follow Martha's. And so he starts with Martha's, and then he starts putting in the priorities of the others. And he's got to meet with these people. He does it at home. But in the office, you meet them on the phone and on Zoom and on all those things. And eventually you make a design, and you make 4 little sketches of the different pieces to make these people happy. And somebody says, oh, what a wonderful design, we're going to build your design. And all of the projects that are in your exhibition room have that characteristic, all of them. Because it works. Why shouldn't it have that way? It's at that size. But let's get bigger and see what happens. Now we're going to be over here. And all of a sudden, we've got a board of directors. We've got the mayor and the head of the sewers and the head of the water system, and the head of the parks and the head of the roads, and the guy who owns this one and the lady who owns this one. And they don't agree on what they want. And they'll meet for a little while, and they'll call you in, and you'll discuss with them, and they'll also have 4 different or 5 different or 6 different versions of what they want. And so you're going to do something very similar. Why? Because you did this one, and it worked. So you're going to say, okay, this time, however, I'm going to not just pick Martha's, I'm going to make a small design for any one of them, meet with them all, and we're going to decide this is the one we should carry forward. And so we're going to carry it forward in exactly the same process. We're going to have a design. We're going to make 4 little drawings, one for each of them. They're going to say, wonderful, but then we have to divide up the work so that each of them has a set of tasks for their specialty and a set of subcontracts, and then they're going to build this. So the design method basically works, but the number of meetings increases. Let's get bigger. This time, we're dealing with Athens, Georgia, or Ames, Iowa. And we've got a bunch of people in Ames, Iowa called the council or the directors or whatever the hell they are. And they don't agree for the same reasons. Why? Because they each have interests. The university, the town, the commercial people, the traffic people, the sewer people, the water people, the corn farmers, and the region outside. They each have their views. And this time, it's more people with more priorities and more requirements, and you face this problem, and this is the problem. You're going to start out on a design. How you pick that one, nobody will ever know. But you've had a hell of a lot of meetings, and you promised this one that, and you promised those 2 people that, and you promised this people, except it didn't work. And then you've got to start way at the beginning. Why? Because you promised this one, and it didn't work. So this one has to become this one, which, as you see, is different. And now you've got to be going that, and if that happens again, you're going to start again. And it doesn't work. This project could take 10 years. So you have to do something different. This is where geodesign works, because it's co-design in a collaborative team, meaning all of these people have to agree that they want one design coming out. And with negotiation is the design method, and the design will emerge. It doesn't begin with your concept. It ends with a concept, and it's not yours. It's ours. And so what you're doing here, and this varies, as I will show you, you set a group of priorities, and each one of them produces a design, except in the following way. Because you know there's one coming out the end, it's in your interest to get other people to do what you're thinking. And so instead of keeping these secret, everything is public. Everybody's design is public. And if you have a good idea, and she knows you have a good idea, it's in your interest that she steal it. Because in the end, it's in 2 designs, and everybody else is in 1. So think about that. You ought to look at each other's shoulders and not keep your designs secret, which is what you tend to do in a competition. Because you want everybody to do what you're thinking. So it ends in the final design. So informal negotiation, meaning this design ends up in that design, is really, really important. And when you get a bunch of designs, you then organize a negotiation. And there are rules for how you do that to make one design. And once again, at this scale, you have to have specialist groups that have to build that thing. It is I'm going to show an example of this done at this university, of that one. This is done in a collaborative environment with the assumption that people disagree in a framework. And there's one other complication, and that is, if these are the people of the place, these are the design professions, these are the geographic sciences, and these are the information technologies, and they're all collaborating on a design, regardless of how it's organized, the faculty will never know who did what, because it's collaborative. How do you know in a collaboration who did what? And so the grading system of the university, which grades individual students, doesn't work for collaborations. It's a very big problem. It can't be fair because the faculty doesn't know. The students know. And the students can't grade themselves. But they grade themselves by hiring their classmates 10 years from now. That's a very big academic problem, but it's we who are the problem for the students. Look, these are the kinds of projects which this works on. It works on multiple constituencies, A, B, C, D, and F. This simply means people don't agree. They have to negotiate, they have to produce a design. And there are lots of types. This is the sensitivity problem. Should we build a new ring road for Ames, Iowa, or should we not build a new ring road should we build a new ring road for Ames, Iowa, or should we not build a new ring road for Ames, Iowa? And how do we get a compromise or a decision made for that? And this is the multiple jurisdictions. I'm also going to show a project here that is a multiple jurisdictions problem that many of my front row friends worked on, actually. This is, do the counties tell the region what to do? Or does the region tell the counties what to do? And how do you solve that problem? And if you're working at the scales that I'm going to lead you toward, that's the problem. Technically, this is easy. The work that's out here, starting from about here, moving definitely to about here, is serious. The techniques that I'm talking about are most useful at the beginning of thinking about and deciding on the strategy of what to do. It does not normally produce a precise final product. Rather, the product of this kind of thinking is it could or it should be something like this. In other words, these techniques are really good at the very first stage of thinking about a problem. They're not good at working drawings. And if building something is your objective, stay away from geodesign. If saving something is your objective, it might be useful. It's complicated. There are multiple systems and geographic scopes and uncertainties. The methods should fit the context. Its technical support has to be flexible, iterative, transparent, and rapid. It's dynamic. The changes are sets of policies, practices, and projects. Geodesign has to rapidly move from infinite possible designs toward a socially, environmentally, and economically feasible set. And it's collaborative. The natural language of geodesign has to be easily understood by all. The geodesign endgame must support informed negotiation by people who aren't professionally trained. In other words, professional jargon is out. If you don't understand it, you're not doing a good job of communicating. And the design will emerge. Now, for some quick examples. In 2015, Brian, Rosanna, Allison, John, were thinking about Wormslow State Park. And at the same time, Lupita McLennan was talking to people here about doing a study of Chatham County, Georgia, basically Savannah's county. And we decided to do a workshop for 2 days, thinking about industry, tourism, social change, climate change, water, groundwater, history, visual. We were hosted elegantly by your friends who own Wormslow. And this is what we did. A group of people across the university, from the county, some visitors, were met. When these people had to describe themselves, almost everybody had more than one of these characteristics. I mean, you could have an ecological science who knew information technology who lived in Georgia. So you could have more than one of these characteristics. We met with the people, Fred Marland, who Bruce worked for when they did a study of the, let's call it the green infrastructure of the state of Georgia. They did that by satellite interpretation in the 1970s. In the 1970s, you had his company, Laurie and Bruce, were studying the whole state ecologically. And he explained to us about the Wormslow Islands. This was 2 days. We made a set of evaluations for the vulnerability and the attractiveness, the vulnerability of these systems and the attractiveness of these systems. Green means change it for the better. Red means it's working well. Stay away. Don't touch those areas if you can help it. We then divided into 4 groups, one making a climate-oriented design, environmental-oriented design, the planning structure of today, and the development people who wanted to change the place for new houses and industries. And each one of these groups made diagrams of projects and policies. It took them about half a day to get oriented. Teaching them the software took about half an hour. And by the end of the first day, they had a whole bunch of projects mapped out and specified. And they had these designs about 11 o'clock in the morning on the second day. And we put them all together on top of each other in the computer. And what you see here is when you see a clean color like one of these, it means they agreed. Everybody agreed that that should be protected. There's the legend. But when you see muddy colors, it means they disagreed. So there's a level of uncertainty when you put a bunch of designs together. Just graphically, you can express it. If it's muddy, people are disagreeing. But then they started to negotiate. And so we had one negotiation between climate and environment and one between planning and development. And this was the result of the policies and projects of these 2 groups, basically saying stay away from the coastal zone with your development. And then these people, the planning and development, basically found out that they couldn't solve the requirement of doubling the port of Savannah in Georgia. In other words, the effect of a change in Georgia was in South Carolina. That was really important. And then they negotiated between those 2 teams. And they came up with, that's the existing conditions, and there's Wormslow. And that's the new conditions, and there's Wormslow. And Wormslow is in a very interesting place. Let's remember this when I show you the second project, because what we did not do is we did not raise sea level. The collaboration that we formed now has 240 schools in which we have at least one person working with us on these things in 61 countries and 130 completed projects. This is what we've agreed on. We've agreed on, this is about to change in a way. We've agreed that all the projects would deal with water, agriculture, green infrastructure, which landscape architects tend to specialize in, energy, transport, industry, institutions, and housing, and you can divide it up. That we all would agree on square sites. Why square sites? Because no matter what the shape of your site, you'll have somebody that's over the boundary. It's really important. I saw a map this morning in Rosanna's class that was bounded by the boundary of Ames, Iowa, and I said, what's the boundary? But surely by 2050 it'll have changed, and surely you want to know what's across the boundary, like their garbage dump. We agreed on 2035 and 2050 as time frames, and 3 scenarios: early adopter of innovations to non-adopter of innovations, and a late adopter. And we agreed to use the United Nations Sustainability Development Goals as one way of judging the quality of our designs. Those are international treaty goals by most countries. We agreed that everybody would present their designs in the same format, exactly the same format. And Brian was very instrumental in that, getting this thing done. And he and I edited all the projects. And so this is the University of Sao Paulo. Let's open up the river that runs right through Sao Paulo. That's the site plan. That's the design drawing. That's here. That's here. But it's only one of the options that they had to design. And when we had our meeting that year, we had several people who designed those things. We had urban expansion problems from the United Arab. We had my project with Tess in London. We had Sao Paulo. And when we started looking at 50 projects, and you see them all in the same language, you say, well, wait a minute. This is the expansion of Chiang Mai in Thailand. This is the expansion of Al Ain in the United Arab Emirates. This is the expansion of downtown Minneapolis. This is a river in Brazil. This is a river in Korea. This is a river in Argentina. This is Portsmouth, Rhode Island, with flooding from the sea. This is Virginia, but it's a problem in Ethiopia. No, not Ethiopia, in Ghana. And this is Virginia Tech at Virginia Beach, in the same language, on the same problem, in different schools, talking to each other. And we figured out, after analyzing them, that the continents had different priorities, but in general, green infrastructure was number one, high-density housing was number two, water was number three, energy was number four, as the things of greatest concern globally across these schools. What if we do a bigger project? This scale. It's the same basic strategy, but there are more of them, more people, and you have to produce a sub-plan for each component. In other words, look here. There's only one city here, but there are 1, 2, 3 cities here. And what if there were 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need to not only do a general schema, I need to do a sub-schema for each of those and send that to them so that they're happy. It gets more complicated, but it's actually the same process. And this is what Rosanna and Allison and Brian and John and others did here in 2016. Lupita got the 10 counties in the coastal zone, each one of them, to send somebody. Well, one county didn't come, and you were the county. Brian made believe he was from some county in Georgia. They had to figure out how to work together because the Regional Coastal Commission had to provide a plan for them to work together. But they had the right to make the plan. That's called a multi-jurisdiction problem. And it raises the question, does Lupita tell each of them what to do, or do they tell Lupita what to do? And the answer is both. It's a nice place. You've been there. But it's going to change. The scenario for 2050 is, this is Brian's work. 300,000 new people. 100,000 people to be displaced by ocean rise. 200,000 new housing units. 2,000 acres of new commerce. The supportive Savannah doubles in capacity, another 3,000 jobs. The Camden Spaceport proceeds, 2,500 jobs, needing another 2,000 housing units. This is the priorities for protection of the landscape. The red ones are already protected because of the good work of Laurie and Bruce and others in the 1960s. However, this is the forecast ocean rise from NOAA, from the National Oceanographic Agency. And the good governor of Georgia told the University of Georgia, you may not consider and even talk about climate change 4 years ago, which is one of the stupidest things that I've ever heard. Well, if you look at this map and you look at this map, you realize that there's a problem. So they looked at all of these systems and they made a set of maps. This was a two and a half day workshop, I think we did it in. Yeah. It took about a half a day to get organized. Again, we had people from all over the place, and this could be done by students easily. And they were a very good group, actually, to be collaborating. We met with them. We talked about the place. This was Brian's drawing of the relative scale of change. We discussed how the thing works. They went about making diagrams. It's just drawing diagrams and saying this is a new housing project, and this is a new industrial zone. It's not unlike pencil and paper. And they each made a plan. Each of the counties made a plan. And this is the first set of designs on the second day of the workshop. That's their objective. They didn't do that. This is their design, and this is their design. That's the first day. On the second day, in the middle of the day, they made their second and third designs. Now look at this pattern with squinting eyes. Just look at it. And you'll see that's the second day. That's the first day. That's the second day. And by looking at each other's work, they started to become more similar, which is exactly what you want. And then they started to negotiate. This is the negotiation between the two groups doing regional plans. And they ended up negotiating in an organized way, supported by software that tells them where to negotiate. And then Lupita, who's the head of the agency, met with each of the county representatives and figured out what they wanted and how that fit in with the plan. She negotiated from the regional perspective to the local perspective. She, by the way, now is the planning director for Salt Lake City. And this is the final design, but the most important thing is this part. Look at this. This is the optimum green infrastructure plan done by Ryan Perkle, who's now at Esri, by a computer program that says the animals in Florida have to get to South Carolina. How do the animals in Florida get to South Carolina? By the way, who wants an alligator going through Georgia? But that's the problem. All right? And this is the best way. But when we ran a computer program to say which development would go where, these red parts of the optimum way were being destroyed by agricultural policies, converting pines to pellets to send to Europe for heating, and trying to figure out what to grow on the remaining open areas, which the animals won't cross. So the agricultural process, feeding energy to Europe, changes the process for the animals in Florida going to South Carolina. And therefore, we reran the open space plan, and now it's the light green ones that are there. And this should satisfy the governor of Georgia, who doesn't want to deal with climate change. But we decided to increase climate change. And so we reran the optimum design again, knowing that we were going to lose by ocean rise some of the best areas that they want to go. The shortest way got lost, across near shore land. And what I want to do is just toggle it. Just go back, go forward. Now, watch this. Forward, back, forward. Go back. Look here. Look right in there. That's the original. That's one. That's the other. In other words, the effect changes the design. And if you had done the first one, you'd be wrong. And this is the history of the design. This is the green infrastructure now. These are the protected areas and the connectivity corridors now. These are the ones lost because of future changes that are designed or forecast. This is without ocean rise, this is with ocean rise, and this is very different from this or this. So if you were designing a green infrastructure space system now, based on data now, and didn't think about data then, you'd be making a mistake. Because the problem isn't set up right. Think about that. So, in 2015, the problem was Wormslow State Park and the design of State Park in Wormslow. Are you going to build it now, or are you going to build an isolated island in the middle of ocean then? And which is the real design problem? But what if it's the whole world? And this is something that Brian and I and a dozen other people are now working on, how to set up methods and technologies to study the whole world and the most, not this scale, but probably in here, the scales in here. That's what we think are the important ones. I'm going to talk for another 15 minutes, fast. We're going to try to convince as many of our colleagues in the collaboration, including the University of Georgia, to join us. This is a map of the amount of geography which has changed in my academic life. I taught my first class as a graduate student at MIT in 1960. This is the concentration in the atmosphere of carbon dioxide and methane, and this is where the carbon dioxide is coming from in the main, and this is where the methane is coming in the main. And it's dramatically changing your climate. It's not your geography that's changing, it is changing your geography. And you can help it or you can hurt it. There's now this much carbon dioxide, and this is how much there was until the Industrial Revolution. And there's this much methane, and there's roughly this much back before humans were on the earth. The temperature forecast here for the year 2100, this is 2050, is at a time when there weren't human beings on the earth. And if you don't think that that's serious, you're not thinking ahead in your lifetime. These in brown have to import water now. They do not have water. These areas in red by 2070, if the forecasts are right, and let's assume they are for a minute, the ones in red will have a 50% more or less reduction in their agricultural productivity. The places that will increase, Russia, Canada, Scandinavia, parts of Chile, parts of southern Africa. The birth rate will slow down, but it has a high variance. The places in yellow do not have replacement birth rates. The places in blue have exporting birth rates, meaning that if the places in blue are in this red zone, they're going to export their people because they won't have food and water. This study is the most important of them all. It's for the American Academy of Sciences of the United States by Xu and others, and it's called the Human Climate Niche Suitability. And if you look at this map, which I don't have a sharp copy of, but it doesn't matter, they assume that if the population of the world is 10.5 billion, that 1.5 billion people will consider migrating, the ones in red. And if you look at that map, you'll see Georgia's on that map in red. Why? Because it won't have sufficient water and local food production. It'll be very hot and very humid. It might not be pleasant. And it'll have alligators. What we want to do is we want not to go to 2050 and have only 1.5 increase Celsius. We want to actually, by 2050, reduce carbon in the atmosphere and lower emissions, and we want to start between now and 2030. In other words, the people who are negotiating this may have a realistic or even unrealistic view of politics and economics, but they're too slow. If we did now everything that should be done, the climate will still have changed, and California will still be burning, and Australia, and the people who don't have water will still not have water. We're building a set of technologies between Esri, Geodesign Hub, science, to be used globally and locally and globally and locally and globally and locally and globally and locally and globally and locally. This is Peter Droege, me, Jack Dangermond, figuring out how to do it. We haven't finished figuring it out. Brian and I exchange emails several times a day. But we're close. We actually are very close. That's not important. It is important. We're merging technologies, and what our aim is to provide the technology to every school that joins us free for the fall semester of 2023, to be able to study things at this scale. And we're funded to do that. What we're going to do, and are soon going to do, really soon, we're going to look at the critical conditions requiring climate actions related to water, biodiversity, agriculture, energy, transport, and urban development, and provide guidance to local designs that take on this set of problems and any others that they want to subdivide in the language of the IGC, but adding climate actions to their designs. We're then hoping to get 50 to 100 of these, analyze them, and be able to then figure out where, at a global level, on ecosystems rather than on countries, climate policies ought to be adopted. Our colleague at the Liechtenstein Institute for Sustainable Development. Liechtenstein is a country in Europe, if you don't know that, and has a university, and a guy who's also a Kevin Lynch doctoral student, like I was, who spent his life working on sustainable development methods. And he's organizing them into a list. Some of them come from the IPCC, the International Climate Group. Some of them come from NGOs that have been studying these areas. We have global maps of potential wind power. We have global maps of priorities for conservation. We have global maps where 1 billion trees should be planted. We have estimates of where the most big cities are going to be and where they are and how much they're going to grow. That's a design problem. We're working on 400 mixtures of climate, topography, ecosystems, and we're working on them at a scale of 1 kilometer square. In other words, the data are publicly available global data that are now public at 10 meters square. This room is probably 6 to 9, 10 maybe pixels on a global data set that is publicly available. And there's a group of 60 people working on making sense of it. So Ames, Iowa, go to a computer, clip out a square, and you've got your data, you've got most of your analysis, you've got the climate things, make a design. We're working to include the continental shelf, and this is the base map. This is the base map for the design. This is the base map applied to Southern California. Brian, tell me once again, what are these pixels?
Those are carbon stocks and carbon emissions. The carbon stocks are the amount of carbon that is being sequestered, so it's being taken out of the atmosphere, and the carbon emissions are the amount that's being pumped into the atmosphere, so the piece that drives climate change.
So some are pluses and some are negatives. And this will be changed if, let's say half a million Central American migrants find their way into Southern California. 500,000. That's a small number relative to what it should be. So that will change the land use pattern, which will change the reflectance, which will change the carbon emissions, which will change the ecological systems, which then is reflected globally. And we think we can keep track of that. And that's our test case, by the way, hopefully in January. And we hope these people participate. Because this is the European change. This is the forecast do-nothing scenario, the changing landscape of Europe. And I'm working with the Portuguese, who basically have a forested landscape with villages, which is not going to be forested. And they sure as hell don't have water, because they get it from Spain. And Spain isn't going to give it to them, because they export fruit to Europe, which is water. And this is Georgia. This is from the Clark Laboratories using the same type of technology. Now, this is Georgia in 2015. This is Georgia in 2050. 2015, 2050, 2015, 2050, 2015, 2050. And that's the project that Rosanna and Allison and Brian and John and others did in 2016, when we didn't deal with climate change and we didn't deal really with the ocean rise. And it strikes me that that presents some interesting problems. For example, what do you do with the Appalachian Trail when the forests change? What do you do with pine trees in Georgia when you're cutting them down for European heating? And they sequester carbon. So there's a problem, and you can solve that problem. And the difference between what they did in Savannah and what they did in the coast of Georgia is this time we're going to apply climate change systems to these projects and make it part of the project. And you do it by pressing a button, but you have to think about it before you press that button. And your project will be the center of the world, regardless of where it is in the world, because the technology allows us to make your project, no matter where it is, the center of the world. And we can feed it into a climate model if we gain access to it. We can estimate it. And we can ask very important questions. Can climate change be mitigated by a global climate action design? Can climate change be mitigated by concerted local action? Maybe the answer is no. How effectively can climate change be mitigated by conservative local action by 2030? Again, we don't know. We don't know what our colleagues will be thinking. But that's what we want to do. We intend to do this part around New Year's and maybe into February. We intend to teach people how to use the technology and give it to them free in the summer. We're looking for teams that are going to take on a large project. I don't care how large it is. I don't actually care what it is. In the fall of 2023, we're going to analyze them in the winter of 2023. We're going to make a global design for 2030 and for 2050 in 2023-24. We're going to put these into a climate science model if we gain this point. This line means we're not sure we're going to be able to do that. And that technology can be used for the next 10 years. And it costs nothing. It costs time, it costs energy, it costs effort, but it doesn't cost money. And we think we can do this. And so we're inviting any team that's interested in the whole world to join us, and we'll support them with tutorials. And I want to end with this slide. I thought to myself when I was making this lecture, what would these two people think about my lecture? And I can tell you what they would think. They would think, let's do this. Why? Because these two people were adventurous. That's why. Thank you.